Good morning, students. Our next topic is compactification of a topological space. So let us define what is compactification of a topological space. Let us take X with topology tau be a topological space. Then compactification of this topological space means a compact topological space with a dense embedding. That compact topological space we have denoted by X star with topology tau star, and here I from X into X star, that is a dense embedding. Dense embedding means this mapping I is 1 1 continuous open, and the closure of I of X, that is the set X star. So if this condition is satisfied, we say that this topological space is compactification of the topological space X tau, or we can say that the topological space X tau is embedded in the topological space X star as a dense subspace. It means this topological space is homeomorphic to a dense subspace of this topological space. Now, next definition. What is Hausdorff compactification? The compactification X star of the topological space X, that is said to be Hausdorff compactification if, in addition, this topological space X star with topology tau star, that is T2, then we say that compactification is Hausdorff. Now, the next theorem is every Tikhonov space has a T2 compactification, and converse is also true. Means if a topological space has T2 compactification, then it is Tikhonov. So first of all, let us take the topological space X tau has T2 compactification, which we denoted by X star tau star. Then by definition, this topological space is compact and T2, and the mapping I from X into X star, that is dense embedding. Now we are to prove that the space is Tikhonov. Now to show that X is Tikhonov, because X is homeomorphic to a dense subspace I of X of the topological space X star tau star, and this topological space is compact and T2. Therefore, the topological space X tau, that is Tikhonov space. Now we do the converse part. Conversely, we are given that the topological space X tau is Tikhonov space, and we are to prove that X has T2 compactification. For this, let us define a collection Bx of all those functions which are defined from X into the unit interval I. This is a collection of continuous functions. We already discussed in the embedding theorem and embedding lemma that this family distinguishes points as well as points from closed sets. Now let us take Z is the product of the unit intervals. Here IH is unit interval, which we have denoted by I. For every H belonging to the family B of the continuous functions from X into the unit interval I. Now this unit interval, that is compact, and by Tikhonov product theorem, product of compact topological spaces is compact, so Z is compact. Also, Z is T2 because this is the product of T2 spaces. So by productive property of T2 spaces, Z is T2. Now Z is compact, Z is T2. So we can say that Z is compact as well as T2. Now we can use embedding lemma. By embedding lemma, the mapping E from X into Z, that is an embedding. Now let us denote the closure of the set E of X by beta X. Now we claim that this beta X is T2 compactification of the topological space X tau. Now from here, being the closure of Ex, we can say that beta X is closed and it is a subset of compact T2 space Z, and therefore beta X will be compact. Also, beta X is the subspace of Z and Z is T2, so beta X is T2 also. So if we restrict the mapping E to beta X, then E is an embedding which is a mapping from X into beta X, and also E of X closure, that is beta X. So we can say that beta X, that together with the mapping E, that is Hausdorff compactification of topological space X tau. So this completes the proof of the theorem. Next we define Stone-Check compactification. If we take a topological space X tau, which is Tikhonov space, and beta X is its Hausdorff compactification, then this Hausdorff compactification of the Tikhonov space X tau, that is called Stone-Check compactification. Now next we do the theorem based on compactification. Let X tau be a Tikhonov space. Then we prove that this Tikhonov space has Hausdorff compactification denoted by beta X, which has the following property of extension of continuous maps. If we have Y with the topology tau dash, a compact T2 space, and a function f from X into Y be a continuous function, then there exists a continuous extension of the function f given by f bar, which is a mapping from beta X into Y, such that the composite of the mapping f bar with E, that is the mapping f. To prove this theorem, we require two lemmas. So let us discuss one of the lemmas firstly. According to this lemma, if we have A and B, two sets, and f is a mapping from A into B, IA, this is the collection of all those functions x which are from A into the unit interval I. IB, this is the collection of all those functions y which are defined from the set B into the unit interval I. Then we are to prove that there exists a continuous function f star from IB into IA such that f star of y is y of f, where y belongs to the set IB. Now, in order to prove this theorem, first of all, let us define the function f star according to a requirement. Let us define it from the set IB into IA. Let us take an element y from the set IB. Now, by definition of set IB, y is a function from the set B into the unit interval I, and therefore the composition of y with f, that is a function from the set A into the set I, and the functions from the set A into the set I, they belongs to IA. So we can say that the function YOF belongs to the set IA. Now let us define f star of y by taking composition of y and f. Now we claim that this mapping is continuous. Let us take an element A belonging to the set A, and we define the ith projection from IA into the unit interval I by defining PA of x is equal to XA. In the same way, let us define bth projection by taking an element B from the set B and defining QB as a bth projection from the set IB into the unit interval I by defining QB of y is equal to y of B. Now, in order to prove that the function f star is continuous, it is sufficient to prove that the composition of ith projection with f star is equal to the projection QB. Now, f star is a mapping from the set IB into IA, and PA, ith projection, that is a mapping from IA into the unit interval I. So the composition of these two mappings, PA of f star, that is a mapping from the set IB into I. Let us take an element y from the set IB and let us find PA f star of y. Now this can be written as PA of YOF. Now by definition of ith projection, PA, this is YOF of A. F of A, that is B. So we get Y of B. Now by definition of bth projection, QB, Y of B is image of Y under the mapping QB. So this proves that the mapping PA of f star is equal to the bth projection QB. Now this mapping is continuous because projection map is always continuous. So this proves that the composition of PA with f star, that is also continuous. Also, the mapping PA being the projection map, that is continuous. So we can say that the mapping f star is continuous. So this completes one of the required lemmas, and tomorrow we will discuss the proof of the main theorem as well as the second lemma.